Hello and welcome back to the lecture on applied econometrics. So we have been talking about the different types of probability approaches. We spoke about classical approaches to probability. Now in this lecture we are going to talk about the frequentist approach of probability and we will see how they differ. Now let me ask a couple of questions before I begin. For example, let's say if I want to understand the life expectancy of an Indian who is 25 years old and say I'm an insurance company and I'm really interested to understand the life expectancy of someone for a given age, the number of years someone can live, because I have to kind of decide the insurance premium based on that life expectancy. So if I think of using classical probability rule, it will not be able to help me because I need to get some background of the life expectancy of Indians, and that might actually vary if I go to England, and that might actually vary if I go to some other country, right? So for that purpose, we actually need to calculate probability using historical data. And when we calculate probability using historical data, that approach is actually called the frequentist approach of probability. We basically count the frequency, count the numbers from past data. Now actually I'll tell you a story before I begin, and that story goes back to the time of Mahabharata, and we will see the examples of frequentist approach to probability back in that time. You might have heard the name of King Nala, and King Nala is a pure and virtuous man. He is a king. He is married to his wife Damayanti. But there was a evil king whose name is Kali, and Kali is his king of the neighborhood kingdom. Kali was jealous, and Kali wanted to snatch Nala of all the things he had, but he never had a chance because Nala is a virtuous man, so he is a pure man. Now there was something in Nala's character that was his weakness, and that was gambling. So Nala used to gamble, right? Kali knew it, and Kali wanted to actually defeat Nala on gambling. So Kali invited Nala in one day to his palace with all due respect, and he invited Nala to actually play a game of gamble with him. And Kali is a shrewd man, and what Kali did is Kali gradually enticed Nala into this game. He kind of made him like totally forgetting his reality. So what he did is he made Nala win in the first bet, in the second bet, in the third bet, and deliberately Kali started losing his like elephants, his horses, his army, almost everything. So when Kali was almost Kali lost everything except his kingdom. So the last bet, Kali said, well Nala, you are doing really well in this game, and I want to take a last chance, and basically I want to bet my kingdom, and of course you also have to bet your kingdom and your wife. Now Nala, being enticed to that, he actually ended up betting his kingdom, and what happened is in the last game Kali won, and Nala lost everything in that last game. Losing everything, Nala actually started wondering. He has nothing. He has he has no home. He's traveling in jungle, no identity anymore. Nala happened to, it happened for many years, and it was a lot of tragedy in his life, how he spent his time. After many years, Nala actually met a man named Rituparna. Now Rituparna is a man who knew how to play gamble. Rituparna somehow befriended Nala, and Rituparna actually told Nala a secret, and he whispered that there is a way I can actually ensure if I win gamble or not. Nala didn't believe that because gambling is pure gambling, it's a matter of chance. Rituparna then asked Nala, can you tell me how many leaves are there in the tree? And Nala said, it's very difficult, I have to count the number of leaves in the tree. And Rituparna said, no, I can tell you the number of leaves in the tree without even counting. Rituparna said, Nala didn't believe him, and Rituparna actually gave a number to Nala that this many leaves are there in the tree. Well, Nala didn't believe that, and it was in the evening. What Nala did is that he actually started counting leaves of the tree throughout the whole night. And in the morning, when Rituparna got up, Nala counted all the leaves in the tree, and Nala came back, and Nala said he was surprised. He said, Rituparna's prediction is almost pretty close to that. So how Rituparna did that? So how Rituparna did it was very simple. So Rituparna simply took one, say, stem of that tree, and he counted a bunch of, you know, like leaves on that stem, and he made a sense of how many stems are there in the tree, and he made a prediction. So this is essentially, you can say, you know, some evidences of you know, how people used that frequentist approach to calculate, you know, the very early days of calculating probability. And this is one story that mathematical historian, his name is Ian Hacking, he was actually trying to figure out the genesis of you know, probability of the frequentist approach, and he found this evidence in Mahabharata. Now this is a story, but actually it got a shape in commercial life back in 1666 onward, like when we had London fire, Hamburg fire. So, you know, the city was kind of demolished in fire, and people sort of, you know, started to rebuild the city, and that was also the genesis of the insurance industries, because, you know, the people, the business people, they actually found an opportunity that, you know, if you can insure people for all these kind of risks, so they actually would pay you a premium, and you can actually, you know, build a business around it. Now that was the beginning of actuarial science. I mean, the example I gave at the beginning, I want to understand the life expectancy of someone, you know, because of a given age, because I want to charge a premium on you know, in case on his life. Basically, if he dies, I have to pay back some money to his family. So these are basically the examples of the frequentist approach to probability. And as you see, I mean, all the classical, you know, the rules of probability that we have learned after classical approach, they are all valid here. Only thing is that we are deriving the probability out of data. So with this, I will actually do an example, and this is the data set that I have, and this is I have taken from somewhere, and let's say we are talking about town XYZ town, and this is the data for COVID related, you know, death in the town. Let's say I have this data for different age groups, and I have number of deaths in that age group. I also have number of deaths with, if they have any condition like the morbidity condition, like comorbidity condition, or they do not have any comorbidity condition, or I do not know why exactly they died. I mean, I do not have any information about their morbidity, I mean, if they had morbidity or not. So let's say this is the table, and I actually want to answer some questions. So let's say the question number 1 is that what is the, you know, let me write down the questions actually. What is the probability? Let's question number 1. What is the probability that someone who died in the age group of 64, I think I had 64 to 75 with underlying condition. So I do not have any formula, like any classical approach formula that I can use directly, but what I can do is I can actually use the data that I have provided to actually calculate that. Okay. Similarly, I will just ask a couple of more questions so that we are conceptually clear on this topic. So the second question is that a person died due to COVID in XYZ town. What is the probability? Let's say, what is the probability that he or she is in the age bracket, in the age of 64 to 75, let's say. So these are different questions, but we can essentially use that data and we can actually get the result. Similarly, we can actually, you know, let's just answer these two questions. Okay. So what do we do here? Simply, the first case, we have someone who died at the age group of 64 to 75 with underlying conditions. So first thing, what is given here is the age group. So I have to actually focus on the age group, right? Age group is 64 to 75. So, this is the age group and with underlying condition, right? The underlying condition is, you know, is 1272. So, how do I write the probability? How do I write the probability? I write, so for question number 1 is, so probability that let us say let me write down the denominator first, probability that he is age group 64 to 75, and on the numerator probability underlying condition intersection age group 64 to 75, right. So, the number is, we already have the number here, it is just you have to plug the numbers here. So, the total number of death is 5151, total number of death is 5151, no sorry, the age group, the total number of, just a second, what is the question again? What is the age group? Okay, yeah. So, died in the age group of 64 to 75, that means total number is 1683, right, 1683, and underlying condition would be 1272. So, I have to just get the ratios. Essentially, we have to understand this concept of how, you know, I am basically intersecting the, you know, different conditions, right. So, that is my question number 1. The question number 2, I asked, a person died due to COVID in XYZ town, what is the probability that he is in the age group of 64 to 75. Now, a person has already died, right. So, I am already having the information about the death, and which is 6839. So, I am talking about the entire, you know, population or all the samples of people who died. So, let us say probability of, say, people died due to COVID in XYZ town, all right. And in the numerator, I will have those who died in the age group of 64 to 65 to 74. So, that will be people died in the age group of 64 to 75. Now, you can, is 65 to 74. You can also think that this is number of people died in the age group of this intersection, total number of people died in the in XYZ town, right. So, it is the same basically, because it will be the same number here, right. So, the answer will be number of people died in the age group of 64 to 75 is going to be how many people? It is 65 to 74, it is 1683 and total 839. So, essentially it would be, in your denominator you will have 6839 and in your numerator you will 6839 and here you will have 1683, right. So, this is how you, based upon the question asked, so you always kind of compute the probability using the frequency that you have obtained. So, this is how you actually, you know, use a frequentist approach of probability. So, with this we will end the lecture on frequentist approach, and in the next lecture we are going to cover a very interesting topic called Bayesian probability, where we will talk about the posterior probability. All right. So, with this we end the lecture here.